Okay, so the last video, and these videos should be watched in order. We developed this formula right here. What this formula does is give us a range of values where we should be able to find the mean of a sample with a certain degree of confidence. And that confidence comes from this value called the margin of error. That value is calculated finding the z-score sigma square root of n. Okay? And so that's how we create a confidence interval where we are sure that if we were to take a sample of a population with this mean, the mean of the sample should fall within these boundaries. Okay. One thing that is also important to notice here, and we didn't do the experiment like we did it for sample means, but actually sample proportions are also normally distributed with a mean equal to the proportion of the population and a standard deviation in the sampling distributions of proportions, which is equal to the square root of p times q over n. Q is 1 minus p, right? So we could have developed the whole theory, but instead of calculating the mean of the samples, we could have calculated, let's say, the proportion of even numbers in the sample. And that data, the data set of proportions, let's say we calculate the proportion in sample 1, the proportion in sample 2, the proportion of even numbers in sample 3. So we get a data set. The mean of this data set is going to be equal to the proportion of the population. All right, this is sample proportion, this is the data. The data is also going to be normally distributed. And the standard deviation, the same way that we did it with the central limit theorem, we can prove that is given by this formula right here. Okay? So the same thing that if we want to create a confidence interval to find out what proportion for samples will fall. So this is a sample right here from a population. And we want to calculate the proportion of this sample. Well, we could say that 90% of the time, the proportion of that sample will fall within the proportion of the population plus the error. And in this case, the error is going to be margin of error, the z-score, which comes from the degree of confidence that you want to have in building the interval, times the standard deviation, but in the proportions problem, the standard deviations is p times q over n. Okay? Okay, so now what we want to do is the following. Let's go back to this formula right here. The mean of a sample with a certain degree of confidence will fall with this interval if we are given the mean of the population. So right here, in this case, we are given the mean of the population. We are creating a range of values that where we have a certain degree of confidence that the mean of the sample will fall. All right. Now, mathematically speaking, we can do this. Let's take the mean of the population from all sides of this inequality. That gives me negative e less or equals to the mean of the sample minus mu less or equal e. All right, let's take the mean of the sample from all sides of this inequality, and I get that the mean of the sample minus e is less or equal to the negative mean of the population, negative mean of the sample plus e. And then when I multiply everything by a negative, I get that the mean of the sample plus e. When I multiply an inequality by a negative, I have to switch it. This is the mean of the sample greater mean of the sample minus e, which can be written as follows. All right, so now what we have here is a confidence interval, but the population is in the middle. So this right here basically is now we are given a sample mean, and we want to estimate the population parameters or create a range of values where we think the population parameter will fall. So let's review this a little bit and what is the interpretation of this. So for example, if we have this population right here, and then we don't know what is the mean of the population. Let's assume that we know the standard deviation. So we take a sample of size n, let's assume greater than 30, a large sample, and we calculate the mean of this sample. Now, if we say that because we're taking kind of a large sample, that the mean of the population is nearby or close by this value, the mean of the sample, we call that a point estimator. So when we take a single sample, we calculate the mean of the sample, and then we extrapolate and say that we think that that should be close to the mean of the population. We have this thing, this mean of the sample is called a point estimator. All right, which is not very good because it's just a single point, it's a single mean. Now what we can do is create an interval around this mean with a certain degree of confidence. So we create a confidence interval. That we do it by adding and subtracting the margin of error. By doing so, now we have a range of values. This lower bound is the mean of the sample minus E. This upper bound is the mean of the sample plus E. With a certain degree of confidence, let's say 90%. Right? So now it gives us confidence that this interval will contain the sample mean. We are that confident that this interval will contain the sample mean. Now, what is the interpretation of that? So let's see. So let's do an example. To do an example of this, let's assume that we want to estimate the mean GPA at a college. All right. So what is the mean GPA at a certain college? So we want to estimate that. We know that the standard deviation is, let's say, 0.2 from past studies. Right? And we want to estimate the mean GPA. So we take a sample, and we, or let's say 36 students, and we find out that the mean of the sample, the mean GPA in this sample of 30 students is equal to, let's say, 2.8. Right? So now, if we use this value and say we think that the mean GPA for the whole population is 2.8, we're using a point estimator. But instead what we should do is create a confidence interval, let's say at the 90% level. So if we do that, then we're going to put 2.8 minus E, 2.8 plus E. We calculate the E, which is 1.96 now. For 90%, we already know that the Z value is 1.645. The standard deviation given square root of the sample size, which is 36. All right. So we calculate that value, and so let me do these calculations right here. So this E is equal to 0.055. So I added and subtracted to this interval plus 2.5 plus 2.8. I get 2.8 plus 0.055. So we created this interval, and basically what we're saying right here is that the mean of the population is going to probably fall within these values, and we have this degree of confidence. It's not a probability, it's that we are this confident that the mean of the population fall between these values. So we have a range of values where we think we can find the mean of the population. However, if somebody else uses a different sample, obviously they're probably going to find a different sample mean. And when they create an interval, it's going to have a different ratio of values. And we're also 90% confident that the mean of the population is here. If a third person uses a different sample, they're going to find a different sample mean, and they create an interval. So we are 90% confident that the mean of the population is going to be in this interval, that the mean of the population is going to be in this interval, that the mean of the population is going to be in this interval. So basically we see that we start narrowing a range of values that we are sure contain the mean of the population, right? So our intervals can get smaller by creating a lot of these confidence intervals and finding a value that is in 90% of them, since we're creating a 90% confidence interval, right? Obviously, when you're tested or assessed on these particular questions, we just ask you to build one, not to build 100 of them, which is what we usually do. All right, so let's write that formula. If we want to estimate the mean of a population using a confidence interval, the formula is as follows. You take the mean of the sample that is given and subtract the margin of error. Take the mean of the sample that is given and add the margin of error. And the margin of error in this case is the z-score times the standard deviation, which is given, divided by the square root of n. All right. If you want to estimate the proportion of a sample, then the proportion of a sample is going to be a proportion of a population. The confidence interval to do that is going to be the proportion in the sample minus the error, and the proportion in the sample plus the error. The difference right here is that the error is the z-value times the standard deviation, but the standard deviation for proportions, remember, that is PQ over the square root of n. These values are the ones that we're trying to estimate, so use the proportion in the sample. All right, so those formulas should be studied. There is a special case for estimating the mean of a population where the sample is small, so n is less than 30, and the standard deviation of the population is not known. So instead of having sigma is not given, so instead we have S, the standard deviation of the sample. So we will study that. So there are certain conditions that need to be met within the sample for these intervals to have validity. But we're going to minimize those to say that if the sample is large and the standard deviation is given, let me see why this went away. And the standard deviation of the population is given, we are going to do exactly what we did here. If the standard deviation of the population is not given and the sample is small, then we're going to do what is called a t-test that we're going to review later. A t-test when we do the exercises. Okay, so that is the idea behind confidence intervals. Okay. Yes. So let's begin doing the study guide. So now let's continue building these intervals. So let's assume that you want to estimate the mean of a population. But now with a range of values with an interval. But now your sample size, still you have a sample. But now let's assume that your sample size is only 10. If your sample size is only 10, then without a lot of explanations, what you have to do, and let's assume that you only have the standard deviation of the sample, you have to get your critical values, which is the values that allow you to calculate the margin of error. You have to get them, instead of getting them from the Z table, you have to get them from a T table, a T distribution. The formula is going to be the same. You take the mean of the sample minus the error, the mean of the sample plus the error, but the error in this case is going to be a T value S square root of n. All right. Remember, if the sample is large enough, in this case when the sample is greater than 30, or the distribution of the population is normal, and you know the standard deviation of the population, then remember we are creating these confidence intervals, and for the 90%, for example, we use these C values of 1.645 and negative 1 and positive 1.645. For the 90 confidence interval, we're using a 95% confidence interval. We're using the Z values of 1.96 and negative 1.96. All right. When the sample is small, then this interval is going to be larger to allow for that level of confidence. All right. So let's see what the difference is. But before we do that, let's see how we calculate this T value. Well, to calculate the T value, you have to use the T tables. In other words, the T distribution is also kind of a normal distribution that depends on the sample size, which is the degrees of freedoms, which is n minus 1. So there is a T distribution for each sample size, which is a little bit flatter than a normal distribution. And it all depends on the sample size n. We calculate these degrees of freedoms, which is n minus 1. In this case, it will be 9. And then you want to find out these T values that corresponds to this 90% confidence. So you want to calculate these critical values. What is used instead is these tails right here, which is called the level of significance. Those tails, which in this case are 10%, or in decimal 0.1. And that 0.1 is spread out in the two tails. So this is a two tails, right? And that's how you get this T value. You go to the T table, and then you find degrees of freedom. You read down until you get 9, and then from the top you have a one tail and a two tail choices for the level of significance. You find the 0.1 in this case, and then you get the value. So for example, again, let's go to the Triola formulas. Let's find out the T values right here, the T table. Don't forget those tables when you take an assessment. The degrees of freedom is 9 right here, and then you move under two tails 0.1 right here, and you get 1.833, right? So that would be 1.833. Notice that this critical value is larger than the 1.645 when we use the that is when we use the C values. So let's compare two intervals. Let's do an example. Okay. Let's assume that for the same population we want to estimate the mean, and right here we get a sample of 36, and we know that the standard deviation of the population is 2, and the mean of the sample is, let's say that is 15. All right, over here let's assume that we have a samples of size 10, and the standard deviation of the sample just happened to be 2 also, and the mean of the sample also happens to be 15. All right, so what is the difference between these two? And we want to estimate the mean of the population, or create a confidence interval at the 90% level. What is the difference between these two confidence intervals? Well, with this one, we estimate that we are 90% confident that the mean of the population is between the sample mean minus the error, the sample mean plus the error. Because the criteria for large sample is met, then we calculate the z-value for the 90% confidence at 1.645, and the error is going to be 1.645 standard deviation of the population 2 divided by the sample size, which is 36. So let's calculate this value. That will be 2 divided by 6 times 1.645, and that gives me, oh my god, this calculator is not even on. 2 divided by 6 times 1.645, so I get 0.55, so that gives me 0.55. And so when we build the interval, we get 15.55, and I guess this is 40.45. All right. Now, in this particular case, sample size is small. We know the standard deviation of the sample, not of the population. So when we build the 90% confidence interval, we take the sample mean and we're going to take the error. Sample mean and we're going to add the error, but in this case the critical value that gives you the margin of error is a t-value. The standard deviation given is the standard deviation of the sample divided by the sample size. So now we need to go to the t-tables. The degrees of freedoms are 9, 10 minus 1, and in the two tails, because this is 90, the alpha is 0.1, 10%. So that t-value is, we just calculated, is going to be 1.833. 1.833. So this E is going to be 1.833 times 2 divided by the square root of 36, which is 6. That gives me 1.833 times 2 equals divided by 6 equals, so we get 0.66. See a larger error, 0.61. So when we add that to 15, we get 15.61, and when we take that from 14, we get 13.39. But the whole point is that because we're using a smaller sample, we have to compensate by making the integer larger to have this particular degree of confidence, right? So you should be able to differentiate between a t-test and a z-test. So let's say z-test and t-test to create a confidence interval for the population parameter, the true population parameter, based on sample size, based on the standard deviation given, and also based on the population where the sample came from. If the population where the sample came from is normally distributed, then it doesn't matter. You can always use a z-test. All right. Now, the next video is a lot of examples on the z-table, the central limit theorem, and then these confidence intervals and the normal distribution.